Hi, Dr. Pat here. We're looking at exponential functions. And so these are the kind of graphs that, kind of a little mellow at the beginning of it, and then they just start zooming off. So things that just really skyrocket. So that's the kind of graphical interpretation we have. And then the reverse way is something that's really steep with a kind of level off after a while. So one's growth and one's decay. All right, so let's kind of play around and look at some functions. All right, what I'm going to do here is just kind of play with some patterns of numbers, just kind of illustrate what happens with exponential functions. But before I actually get into the exponential, I first want to kind of make a connection with linear situations. So we've got equations of lines I want to start with, and then make the transition to exponentials, and hopefully we'll make some sense along the way. All right, so now when I'm looking at this table of data here, I got 6, 11, 16, 21. One of the things that we look when we look at a series of numbers, table of data, we're looking for patterns. And one way to find that pattern is to look at how the change in the numbers. So when we go from 6 to 11, that would be a change of 5. When I go from 11 to 16, that's another change of 5. And then 16 to 21, again, a change of 5. So in this case, I'm seeing that I'm increasing by 5. So I have a plus 5 for each change. Whenever we have a set of data that has the same amount of change, it's a linear situation. So we can make a formula that's in terms of a linear equation. And so for this one, the change right here is the slope. And then our starting value right here at t equals 0, that's our starting value at 6. So for an equation of a line, this 6 is like my b value, and 5 here is like my m value, the slope. So when I'm making that equation, when I'm making that formula, it's going to be 6 plus 5t. 6 is my initial value plus 5t, where 5 is the slope. And I'm using t instead of x. So that's just another variable. All right, so now take a moment. Look at this one. What type of linear situation is this? Well, first, is it linear? We look at how it changes. And if it is linear, then the change is basically our slope. And when you look at this set of data, hopefully you'll see an increase of 8. So going from 13 to 21, that's an increase of 8. And then 21 to 29 is another 8. 29 to 37 is another 8. So we have a plus 8. So when we make that equation, we're looking at an initial value, because at t0, our initial value of 13, and a change of 8. So we're looking at 13 plus 8t. Now take a moment and look at this one. In this case, our numbers are decreasing. But the key thing here is, how is it decreasing? Looks like we're dropping 11 each time. So since we're dropping 11 each time, that means that we're talking about a linear situation. So we have a negative 11. We have an initial value of 87. So we start at 87 and then minus the 11t. And so there would be our equation of that linear situation. So when we're looking at the formula for linear equations, what we have is we have the initial value in the formula, and then we have a number here that indicates how things are changing. We're going up 5, going up 8, going down 11. And so that's how we have our linear situation. It's all about the same amount of change as we go left to right. Okay, now let's take a look at this number. When I'm looking at these set of numbers, I got an increase of 3, increase of 6, increase of, wait a minute, 12? That's not the same amount. So this is definitely not a linear situation. And so we'd have to look at, well, is it something else? Well, if I go from 3 to 6, instead of looking at it as plus 3, how about if we look at it, hey, that's twice as much. So starting here at 3, I can multiply by 2 to get to the 6. And then going from 6 to 12, I would multiply by 2 again. And so going from 12 to 24, multiply by 2. And so what we're looking at here is this set of data to get from one to the next. It's not the same amount that we're adding or subtracting. It's a same multiplier. So we're multiplying. And so we're multiplying by a consistent 2. And so that's what we got going. And then to make the equation of this, well, this would be an equation of an exponential situation, since we're multiplying rather than adding or subtracting. And so to do that, it would be 3 times 2 to the t power. So t is the variable is in the exponent. And we're using this exponential model because we have a multiplying situation. and that's when exponential, that's when it exists. Now, how about for this example? Going from 40, 44, 48.4, 53.24. What's going on here? How do we look at things? Well, one way to do is it's not a consistent amount, so it's not linear. I mean, we add 4 here, then we add 4.4 here, and then we add even more that way. And so basically, it's not linear because we're not adding the same amount. So then what we could do is take two consecutive numbers. So like the 44 and 40. Take 44 divided by 40. What do you get? You get 1.1. Take 48.4 divided by 44, the previous number, you get 1.1. And then same thing with this 5324, divide that by 48.4, it's a 1.1. So when I'm looking at a series of numbers that are not consistently the same amount of adding or subtracting, I'm looking to see if there's a multiplier there. In this case, we got a nice consistent multiply by 1.1. So I've got the number, how it's changing, and then I got my initial value. And so that's where our formula right here for our exponential situation. Our last one I'm looking at, I start with 300, go to 150, go to 75, go to 37.5. Hopefully you'll see a pattern there. It looks like we're dividing by 2 or multiplying by half. So either way you can do this. You can say dividing by 2 or multiplying by 1/2. But there's some kind of a consistency here. I want to look at it in terms of multiplying. And so exponentials are multiplying situations. So I've got my multiplier is a half. I start with an initial value of 300, and so there's my equation. So I've got 300 times 1/2 to the t power. And so that's how we're setting up our exponentials. But hopefully you'll notice in our exponentials and linears, they're very related. In the linear situation, we had two numbers. We had our initial value and we had the number how we were changing. Same thing with your exponentials. You have your initial value, which you're starting with, and then your base of your exponent is how things change. And so our two formulas then kind of relate here. So we've got an exponential model and then we got our linear model. And so I'm just kind of playing using cues this time. And so what we're looking at here is that we have the initial value the same way. And then we also have a number that indicates how things grow. And so for an exponential model, our growth rate, that's kind of an indicator of how much we're growing each time. That would be this whole base right here. And then we also have a slope for an indication of growth. And then we both have this t-value that represents the number of periods. So you may recall this would be like a simple interest situation and then a compounding interest. And so another way to look at our formula for exponentials is ABX. A is our initial value. It's where the graph would cross the y-axis. So it's our y-intercept. It's our initial value, how much we have at time 0. And that's why you see this little data point here, 0, A, because this represents at time 0, you have that A amount, whatever that number may be. B is the base, that's our growth and decay. So when B is larger than 1, you have a growth situation. So your graph will be increasing, will be going up. If B is less than 1, you have a decaying situation, and so then the graph will go down and it will level off. And then of course our x value, our exponent, our variable is in the exponent, and so that's kind of where you're getting your exponential situation. Now if you're into business and you like to compare these things, so I've got one here where I've got a straight line versus the exponential growth. And so you can see that after a period of times, a period of years, your exponential is going to be produce a larger balance at the end than would a linear situation. So that's why simple interest versus compound interest, you want to make sure you put your money in compounding. But also in terms of population of money, population of people, it usually likes to follow initially like an exponential situation. And that's what we got going. So those are the key difference. And then what you're looking at here is doubling time. So for an exponential situation, what you're looking at is that this amount of time it takes to double. So each about approximately 14 years, let's say, this is when this exponential thing is going to double. And so doubling is a very interesting thing because for an exponential, at first your doubling amount isn't very much. You're going from 10,000 to 20,000. So you have an increase of 10,000. But for the next set of doubling, going from 20 to 40,000, we're still doubling in the same amount of time, but we actually have now an increase of 20,000. So it's kind of interesting that in the beginning, our doubling time is still 14 years. So we're talking about a period of time of 14 years. The first doubling is only 10,000. The second 14 years is going to produce another doubling time for 20,000 more. And then the third doubling, after the next series of 14 years, your money would double. It would actually grow 40,000. So you get an exponential. The doubling gets larger and larger and larger. The amount of increase in your balance is larger over a time period. Straight line basically the same amount each time, each pay period. Okay, and then what we got here is just our last idea here about linear growth. And so what we're looking at is a linear growth. That's when we're talking about an absolute fixed amount. So way back when we did the table, we were talking about a fixed amount from one number to the next. It's always the same amount. That's a linear situation. But for an exponential situation, it's relative. And what we mean by that, it's a percentage change. And so it's multiplying the same amount, but the amount of increase, as we saw in that doubling, changes. So the amount changes for exponential. It's the same kind of relative, and that's a percentage multiplier idea. And so that's the key difference between linear versus exponential, simple versus compounding situation. I hope this helped. Take care and have a good day.